the classical orthogonal functions. In this and the next short video, we're going to survey two of the classical orthogonal functions. The functions that come from Legendres equation in this video, and the orthogonal functions that come from Bessel's equation in the next video. These equations will arise in Chapter 6 when we use separation of variables to study PDEs in curvilinear coordinate systems. In fact, Legendres equation will arise in Section 6.5 when we study Laplace's equation in spherical coordinates. So Legendres equation, here it is, it's given in equation 1. And the first thing we need to do is put it in Sturm-Liouville form. And you'll notice to do that, there's a simple procedure. Notice that the coefficient minus 2x of y prime is the derivative of the coefficient 1 minus x squared of y double prime in equation 1. And so the first two terms combine into a single term, shown in equation 2. And we have the Sturm-Liouville form of Legendres equation with w equals 1, p equals 1 minus x squared, and q equals 0. Notice p. P at minus 1 is 0, and p at 1 equals 0, and so we see that x equals plus and minus 1. The boundary points are singular points. And hence the correct form of the singular Sturm-Liouville problem is given in 4, 5, and 6, where for boundary conditions we require the function and its derivative to be bounded at the boundary points, at the singular boundary points. Let me remark about solving Legendres equation. If we look at equation 7, we see it's not a constant coefficients equation, nor is it a Cauchy-Euler equation. So how do we solve for the two linearly independent solutions we know should exist? Well, there's a known method. X equals 0 is not a singular point of Legendres equation, so the known method of solving equation 7 now is to seek power series solutions centered at x equals 0. So the assumed form is given there in equation 8. Basically, the method of solving 7 is to take 8, substitute it in, and use the linear independence of the functions 1, x, x squared, x cubed to solve for the c sub n's. And then once you know the c sub n's, you can substitute them back into equation 8 and you have a power series solution. You then have to investigate where the interval on which it converges. But omitting these details, it turns out that there are in fact two linearly independent solutions on the interval minus 1 to 1. The first one is called p sub n of x, the solution of Legendres equation of the first kind, and the second one, q sub n of x, is called the solution of Legendres equation of the second kind. Hence the general solution of Legendres equation, it's not shown here but we know it, is given in equation 9, a linear combination of the two linearly independent solutions, both power series solutions. It turns out now that by requiring the bounded conditions listed in equations 11 and 12 above, the following two things happen, or three things. The eigenvalues turn out to be n times n plus 1, with n starting at 0. So with these eigenvalues, the power series solution p sub n terminates and becomes a polynomial of order n, referred to as the Legendre polynomial now of order n. And q sub n, the second linearly independent solution, does not terminate. It remains an infinite series, and in fact it's unbounded at both plus and minus 1. Hence, to satisfy the bounded condition in the general solution, where we had a linear combination of p and q, we're going to have to take the coefficient of q, b sub n, to be 0, so that the solution is bounded, as in 14. So let me summarize the solution of Legendres' singular Sturm-Liouville eigenvalue problem. Here it is, shown in equations 15, 16, and 17. 15 is Legendres' equation, and 16 and 17 are the bounded conditions on y and y prime at the boundary, at the singular points of the boundary. The results are the eigenvalues are given by n times n plus 1, where n starting at 0. The eigenfunctions are the Legendre polynomials, n time where n starts at 0. And for all n equals 0, 1, 2, 3, who have a common formula for the inner product of the Legendre polynomial with itself, the answer is 2 over 2n plus 1. It's a simple formula. And we know, in fact, from the singular Sturm-Liouville theorem that the Legendre polynomials are orthogonal when m is not equal to n. In other words, for distinct eigenvalues. And finally, the family of eigenfunctions, the Legendre polynomials, forms a complete orthogonal family for the space L2 on minus 1 to 1 with respect to the weight function w of x equals 1. These are the facts you should know and keep in mind as we apply our work in Chapter 6. The next two slides are just for convenience to show you the first 6 Legendre polynomials, and we'll also have a plot. So here are the first 6 Legendre polynomials. P0 is 1, P1 is x, an odd function, P2 is a half plus something times x squared, an even function. P3 is odd integers, rather odd powers of x. So you'll notice that if p sub n is even, we have an even polynomial, and if n is odd, we have an odd polynomial. Here are the plots of the first 6 Legendre polynomials. The first one is red. That's the horizontal line at the top. The second one is blue, the y equals x, and so on. Here's example 4.3.2 in page 137 in your textbook. I'm going to do the work in the Maple worksheet and show you the results. The problem is to compute the orthogonal expansion of the function f of x that's equal to x plus 1 between minus 1 and 0, and e to the minus 4x between 0 and 1, using, of course, the Legendre polynomials as the eigenfunctions. So we first define the function. It's defined piecewise in Maple, and then we plot the function. So it's an interesting function. It's piecewise smooth, as we can see, in fact. So the first line here is to define the function p that sends n to the Legendre polynomial of order n, and just to make life simpler, right? Instead of writing Legendre p, we're just going to write p. The next line, the middle line here, is to define, it's the formula for the coefficients. C sends n to 2n plus 1 over 2 times the interval from minus 1 to 1 of f times p sub n of x. And finally, we've defined the eigenfunction expansion in the bottom formula there. It's the function that sends capital N into the nth partial sum of the eigenfunction expansion. So in the last slide, here's a plot of the function. It's in black. And then we have the 1, 3, and 8 partial sums. The last one, 8, is the color green, and you can see that it's starting to do a much better job and in approximating the actual function.